exactly. So the question is, what's the best way to inspect parts with 3D systems, and what kind of acquisition techniques are available? Does the object have to be still or moving? And what sort of considerations do you have to take, and where are the weak points of the different technologies? And hopefully by the end of this presentation you'll have an idea of these ideas. So to a novice, let's say someone's at home, a hammer's a hammer. And it goes with a nail, and use a hammer to bang a nail into a piece of wood. The thing is there's lots of different kinds of hammers and lots of different kinds of nails. If you use a sledgehammer with a little pin nail, you're going to probably damage the wood. And really, this is the analogy that I want to say is a 3D vision system isn't a 3D. They're all different, and they all have strengths and weaknesses, and you have to apply the right thing. So not all 3D cameras use the same technology, and they are suited to different applications. So each one has an advantage and a disadvantage. So just one technique might be better for one application, but not as good as another application. So if anyone has been involved in machine vision for a long time, there's been a huge technological development over the years. Camera resolutions have significantly increased, as well as prices coming down. New techniques and advanced algorithms, and especially in the area of 3D, have become market ready. A 3D system 10 years ago was a very complex system to put together. Now you can get smart 3D cameras that take a lot of the difficulty out of them. And with computing power, with 3D you have a lot more data. With computing power getting faster and more processing, and memory getting cheaper, you can deal with this data in a lot better. So no longer is 3D a rocket science, and it can be used with end users with the right training. But you do still need to have the knowledge of know which ones you're going to go with. Thank you. Right. So what do 3D vision systems offer you? They give you the possibility to solve problems in the third dimension. Texture that you wouldn't possibly be able to do with 2D, volume, profile, surface defects, as well as location and orientation. And again, it depends on what the application is you're trying to do. But with 3D, we can directly, accurately locate in real coordinate space where an object is. So things like 3D positioning, 3D completeness, comparing a model to the actual model, volume measurement, and various other measurements in 3D space. So this gives you a quick overview of all the different technologies and the sorts of things that they can do. As I said before, 3D is not the same as 3D. The world, different approaches need different attacks. So multiple methods work on the basis of different technologies where the different components and the camera and the light source are arranged at different angles together. We have stereo vision that very much is similar to the human eye, which I will go into. We have laser light projection, shape from shading. So we have technologies that can go from probably centimeters with things like time of flight, LiDAR, stuff like that, down to millimeters and microns with stereo and laser triangulation. And then we can even get down to sub-micron accuracy with confocal interferometry and stuff like this. So it really comes down to what you're trying to achieve, to which is the right camera technology to apply. Of course, we need to have a specification of what we're looking for, to identify what we want. So one of the first things is let's ask the questions. What's the field of view? What's the relative movement? How large, do I need to look? Is the product moving? Can it be held stationary for a period of time? And how you want to integrate this data into your wider system. And also, what's your expertise? Do you want to build everything from components, or do you want to have a ready calibrated system? And the environment, things like that. Lots of things that need to be taken into a consideration of when choosing the right product. So let's start off with time of flight. This is very, very simple in the fact that you effectively have a pulse of light or a pulse pattern that's sent out from the camera light, and the time it takes to get reflected back is effectively how far away it is. What's very nice about this is that it's instantaneous, so it doesn't need the person can be, or the object can be moving. It is susceptible to things like light, because obviously that light that's being projected mustn't be smothered by the environmental light. You get a single shot image. Accuracy, though, we are only talking about 1 centimetre, half a centimetre about, and probably at the moment we're talking about VGA resolution, might be getting to megapixel at the top end. So, and quite often a lot of them are less than VGA, a quarter VGA. So, where it really comes into its own is things like, I've got a box, is it empty? I've got 5 bottles. Are the five bottles there? So very simple applications. Fill there, is everything done? Is a box nearly full up? You don't need to measure it accurately. It works. Pretty low cost. Product we work with from Odos, which is a part of Rockwell Automation. They do one of these devices, connects with Gigi directly to a vision system, or you can get a smart version where with a web browser you can draw boxes and measure heights. So for instance, I did that bottle application, you can do that connecting directly with Ethernet IP to your PLC. No other software, no other box required. So quite easy, IP rated and good. So that's simple. Then we come to 3D stereo. And again, with 3D stereo, there are different ranges of products from quite high end to low end with different features. 3D stereo is like we see, 2 eyes, and effectively doing triangulation and looking at the difference and parallax between what one eye sees and what the other eye sees. That gives you depth information. Okay, and it's using simple trigonometry, we can get that. But the key point here is we have to see detail. Now, any of you that are skiers and go out in a whiteout, suddenly you can't see the snow and you lose orientation. You don't know where you are. That's exactly what happens with stereo if it's passive stereo. So this is a typical configuration, 2 cameras looking down at a part. What you also find is, because of depending how sharp the angle is, you will get occlusions. Camera 1 is only is seeing one side, but it doesn't see the other side. So this is the first thing that's going to come in. You'll see this being repeated in many 3D applications. Is what we call occlusions. Soon as you're using stereo, you have the risk of inclusions where one of the angles can't see the other. You can't get 3D data at that point, and there are ways around that I will discuss later. So that's a typical setup with the problem. But then we have the problem. Let's look at passive versus active stereo. In the human world, we are passive stereo, so we are looking at detail. So if, again, like that snow, you can't see the edges of the snow, you can't get a depth measurement at that point. So if you have things like a blue floor, you can't calibrate where that blue floor or a white wall or anything like that. But if there is a pattern or detail, you can. So again, if we're looking at, let's say, this mug, we would get where the edges are, we would get 3D data, but we wouldn't get 3D data around the white parts of the mug. So ambiguous surfaces without texture don't work. So you don't get complete point clouds. So you don't get 3D data on every pixel if you need to have texture. So what do we do to get around that? We actually then have a pattern projector, normally in the IR, infrared, so you can't see it, projecting lots and lots of dots or a pattern onto the object. And what that allows you to do is at every single one of those points, you can then get a 3D measurement point. You can't see it, but it's there. So what you then can do is you can work in complete darkness. You can single shot still. Stereo is very good single shot. You don't need to have the object stationary, but you reduce the resolution to effectively a measurement at each dot point. Now there's nothing stopping you combining infrared, active and passive, because if the pattern is still there, you're still getting data where there is pattern, but on a flat surface, this would then give you surface information. So if we look at this pattern, this is now looking at the mug on the left-hand side with an IR image. We are getting measurement points at all of those points. On the right hand, this is someone sitting at a desk with a stereo camera, and we are able to actually get depth information on the desk, on the monitor, the laptop, these flat surfaces that if you didn't have active, you wouldn't get data. You would just get the board data where there is edge information. So, I say there's a big range of products. Real Sense is an interesting one because it really brought the price point down into the hundreds of pounds for stereo. And this little device, 2 IR cameras, infrared projector, and an RGB camera in there, works pretty well for some applications. Not as accurate as some more expensive systems, but they all use a similar kind of technology. So now we move on to another concept of stereo, but this is using 3D laser triangulation. This was probably one of the first 3D technologies that really got stuck in the machine vision world. And what we're looking at is effectively the angle, again, this is using stereo, between a laser line point or a line and a camera. And depending on the setup, geometry of it, we actually get a distortion. So as the laser goes over a boundary, we actually get a step into the camera, and we can then measure that height by that data. So the displacement of the object to that laser line gives you a profile. So if we look here, this is the way, this is I would call components-based implementation. We've got the 3D or the camera on the left-hand side, the laser coming down, and we have to scan the object through, and we build up this point cloud. Okay, of course, this is a very basic system. You really want this to all be calibrated, and there are systems that have all of this built into one go. But from this, we can actually build 3D data. You can configure things in many different ways. If we look here, we can have the laser down, which is the most common way, with the camera at an angle. You can actually do it the other way around, so the camera is looking down at the laser as an angle, or you can actually have it in. It depends on your geometry of what you're looking at, which is best. But you will still suffer sometimes inclusions and things like this. The other challenge we've got is obviously in the environment like today, you've got that laser line, and that's all you're interested in. You're not interested in the camera picking up reflections from everything else. So what we normally do is have a bandpass filter just passing the light color wavelength of the laser through it. So the camera, all it sees is the laser. So then what we do with an encoder, so what you have to have is a carefully moving product or a conveyor belt linked to an encoder to build up lots of these lines to build up the data. That's what we have to do. Back onto inclusions. So what you will also get here is if you've got one system, you will actually, on verticals, you will miss bits of information. Again, let's say this is a compact sensor in the middle here, and again, when it's scanning one way, we miss a little bit of the data because the camera can't see the laser point once it gets behind that. So what we can do is do what's called buddy modes, and that's, for instance, on the right here, a camera that has 2 cameras looking both sides, or you can have cameras coming round to overcome. And some of the best systems actually allow you to calibrate all these together in one go and treat it as one complete system. So now back onto that image that I showed you earlier, what we're actually then able to do is build up this 3D height map based on that laser coming through. We also have challenges though. So what sort of resolutions can we come up with? Obviously, laser trains, high resolution, so 4K is pretty typical now. 4,000 pixels across. If you're triggering every with an encoder, you can build up really high resolutions. But we have to deal with occlusions, and then if you have highly reflective surfaces, you can get errors. And I'll come on to how to deal with that in a minute. But we must have precise linear movement. And you do sometimes have to deal with laser classes and things like that. So light safety sometimes becomes a little bit of an issue. Also, we have to deal with dynamic range, and things have improved massively on this over the years. But effectively, if you're looking at a surface that's got dark areas and bright areas, you will get different levels of reflection of the laser line at the top, as you can see. So what we can use is in the cameras now, technology such as multiple exposures, so you can build up the image quickly, or multi-slope, where the actual sensitivity of the sensor adapts as it gets higher resolution, or high dynamic range sensors. With some of the new sensors that are coming out from Intel now, we are up at true 12-bit, whereas probably 10 years ago we were only at 8-bit. So we're getting a lot more data in the core sensors. So this is becoming less of an issue. But you do have to be aware of this if you've got objects that have big contrasts. Sorts of application, where any kind of application on a conveyor belt works. Is it scanning continuous product? Is it beads? Or is it looking at products as a whole as they go down? But really, they have to be moving. That's the key thing. Other kind of applications here. OCR and code reading on tires, black on black, very difficult to read with a 2D vision system. You've got height there. Doesn't actually have to be very accurate. You don't need to measure the height of it. You just need to detect it. Foil, seals, tubing, tracking products, potato, bulk material sorting. Lots of different applications there. So I think I've really covered all of that. So multiples. So the key thing here is I would think it's because it's been about the longest. It's become the most advanced. So there's a lot of technologies in there. So the first product I'm going to mention here is LMI's product line that we sell. The GoCater 2000 series not only has the laser and the camera in it, it has the processor in it, it has a web browser interface, all the software tools are on it, plus you can actually synchronize all of them together. They're all pre-calibrated. Very simply put them together, it works very, very well. We then also work with a company called Automation Technology. They probably have a more flexible range of built-in sensors that actually go faster, but they're dumb. So they're calibrated, but you then feed that data into a PC-based vision system with 3D software. So tends to be for more complex applications or system integrators that really want to integrate and need specific features. These are the guys that have the MCS family, where you can actually have buddy modes of the two sensors built in to actually deal with occlusions. This is a picture of the user interface on the LMI web browser. So you have a big list of tools, literally drag and drop, mark the points you want to do, connects with the PLC directly, connects directly with robots such as Universal Robots, Fanuc and people like that. So you don't even need a PC to get that data, calibrating very easily the data, the 3D map of the camera into the 3D space of the robot. So then we move on to a different technology, fringe protection. Still triangulation, but this time we're talking area scan. But if you remember what I said on the stereo, resolution was mid. If you want to improve that resolution and get it more, we then start to look at this. Now, what happens here, the object has to be stationary. Instead of having a laser, we have a projector. And we project lots of different patterns onto the object and do that stereo vision on that pattern data. Normally 12 to 16 images which means the object is having to be stationary probably for about half a second. So when you see these, right, you'll see them burst. So this is very good for things like bin picking. There's a lot of places, if you go to people like FANUC or LMI, they've got all these systems. You'll see it go lots of images to get the resolution. But they are pre-calibrated, so this sort of gives you a build-up. You have a projector in the middle, the two cameras doing the stereo, and you have this grey projected gay code. So it starts off with a few lines, then those lines shift into a different position, then shift into a different position. So over those frames, that's why it has to be stationary, you get up a very, very high resolution image. But you have to be stationary. So now this is just an image on the top. You can see those images building through as they step through and get more and more, and the resolution gets higher. So no laser, which is good, no encoder, but must be stationary and takes a while to acquire the data. But in bin picking and stuff like that, it really isn't a problem. So one of the products is the LMI 3000 Gocator, which again uses exactly the same software, the same connections directly into either a robot or into a PC system via gigabit Ethernet. Also with Ethernet, Profibus, Modbus, etc. on there. Very easy way to do it. Again, if you're wanting something a bit more configurable, the Zivid is another good technology. What's nice about that, it's actually a color camera as well, so it gives you color surface information at the same time as the 3D data. And that comes with an SDK that you then embed into your 3D software, such as MVTex, Halcon, or something like this. So now we move on to a different technology. It's still technically 3D, but this time it's not so much. It will pick up very small defects, but it's not about measurement. It's about detection. So surface defect detection is where it really comes in. Where it's very good is where you've got products, let's say like a coin with different materials at different points. You've got surface curvature, variation, color brightness, and stuff like that, with and black edge. So very, very good to that. So it's. But what we actually have to do here. You have to press it again, please. What? 4 more minutes. Okay. So if we actually see here, we actually grab the light fires lights in 4 different directions, and then we process that data to create the images that we want to get. Okay, and what this gives us is independent of the brightness of the inspection objects, drawback, stationary, normally stationary, I'll come on to that in a minute. The cycle time takes time, but you don't get depth information, you get surface information. And this gives you an idea of the images that we've got. On this curvature image, if you can see here on the left, we are looking at the slope, the first derivative, in one direction. On the slope in the second, we are looking at the direction there. We process that and look at the second derivative, and we can really start to find very small, fine defects on that surface. And we also can, with the texture, calculate contamination defects and variations on it. So it's pretty powerful there. Trivista from SAC is the product that we tend to use the most on this, probably the highest end system. And what's interesting about this is they also have methods to use it with line scan. That's where you can move the object. You actually fire the light on a different mode in every single line and then process that data together. But it needs processing to create the image. It's not an image in its own right. So now I'm going to talk probably the newest technology and the most accurate, and we're talking going down to sub-microns here. So this is line confocal imaging. So what effectively we do, we have light being projected through a diffraction point. So basically, when you get a reflection at one point, it's a different color than at a different height at a different point. We've then got the camera looking at that, and when it gets a reflection of a different light, it knows therefore the height of that light. Okay, so it's really powerful. So we're talking, just say, sub-microns here. Very, very powerful. It's like looking through a pinhead. Now this actually application is going to take you through the other thing that this gives you, because it's looking at all the different lights at the same time. It can see multiple levels translucently of different levels in a material. So you can see translucent materials, layers of glass, layers of film, and get all of the measurements in the same time. We're talking, Z repeatability, 0.1 of a micrometer. We're talking very small field of views, 5.5 millimeters, very, very small. And you have to have this on a granite stage to do this, because any movement is going to completely destroy your measurement. But it really gives you an idea of the way that the data comes through. Get all these different levels, and this is used very much in the consumer electronics and into the battery inspection markets. So LMI acquired a company called FocalSpect. In fact, since I did this slide, they've just announced the GoCater 5000 series that has all that technology I talked about earlier, the web browser and all of that, built into this confocal system. So if you're using the GoCater, you can bring this straight into this kind of technology. So it's probably one of the most advanced smart cameras in the world. So I haven't covered everything. There's still a lot more to say, but they, I would say, are probably the most common technologies used in machine vision, certainly online. If you want to learn a little bit more, we do have training sessions at the Imaging Academy. We go into a lot more detail on particular technologies. Also, just to let you know, we can do the feasibility studies. We can even do system design to work with you to select the right components. As you see, we use multiple different manufacturers of technology, so we can advise quite independently. So all I would like to do is say thank you very much, and if you've got any questions, I'm happy to take them.